Welcome to Mrs. Lee's Chemistry Academy. Today we'll continue with atomic structure and periodicity, namely on PES and electron affinity. This is tied to the learning objectives from College Board. The student can explain distribution of electrons, that we can analyze data relating to electron energies. We can describe the structure of the electrons in an atom using PES data, ionization energy data, and Coulomb's law. And we can predict and justify the trend on the periodic table regarding atomic properties. And we can then apply the periodic properties to chemical reactivity. Photoelectron Spectroscopy, or PES. When X-ray or ultraviolet light of known wavelengths with energy h nu strikes the surface of a metal, electrons are ejected from the atoms. The binding energy of an ejected electron can be calculated from the measured kinetic energy, which is equal to the energy of the photon h nu minus kinetic energy. Now, from the PES, we can then look at the relative number of electrons versus binding energy in megajoule per mole and use that information to construct the shell structure of an atom. The intensity of these photoelectron signal gives information on the number of electrons associated with each sublevel. Practice problem number 1. Identify the element from the PES below. Now, on the y-axis, we have the relative number of electrons, which also represents the peak intensity. On the x-axis, we have binding energy in megajoule per mole. Notice how the binding energy decreases as we move from the left to the right on the x-axis. And that does make sense, because for the core electrons that are closer to the nucleus, there is greater binding energy. But as we are moving further away to the valence electrons, they are further away from the nucleus and resulting into lower binding energy. So let's look at the spectrum. The first peak to the left is at 150 megajoule per mole. Now that has about 2 divisions on the y-axis, that's representing 1 as 2 electrons. Now we jump into the 12 megajoule per mole. That peak also is the same size as the last one. So that's probably the 2s2 electron. And then we now go into the next peak, which is quite tall, having 6 divisions on the y-axis. That's representing 2p6 electrons. Then we jump into the 1 megajoule, which has also 2 divisions, that's the 3s2 electron, and the last one with only 1 electron in there, 3p1. And when you add these up, you notice this is aluminum. So this is a recap of what I just mentioned earlier. Practice problem number 2. Explain the relative peak positioning of 1s and 2p electrons in the PES of nitrogen and oxygen atoms. Now we begin with looking at the electron configuration of nitrogen ending with 2p3 and oxygen ending with 2p4. A careful examination comparing the 2 spectra will notice that the 1s peak for oxygen, which is the lower one, lies at 52.6 megajoule, and it is to the left of that of the nitrogen at 39.6 megajoule. Now that does make sense because oxygen has greater effective nuclear charge, resulting in higher binding energy than nitrogen. We then look at the 2p peak for nitrogen at 1.4 megajoule, which is lying to the right side of the 2p peak for oxygen of 1.31 megajoule, because now nitrogen has half-filled 2p orbitals that are more stable. The greater electron repulsion in the 2p4 electron of oxygen, resulting in lower binding energy. Practice problem number 3. Magnesium 2+ ion is isoelectronic with neon. Can their PES be identical? Now, although they both have 10 electrons, but magnesium 2+ ion has 12 protons, while neon has 10 protons. The greater effective nuclear charge in the magnesium ion would attract the 10 electron more tightly to the nucleus than neon, resulting in greater binding energy. Therefore, the PES would not be identical. The peak in the PES of Mg2 plus ion are expected to lie further to the left than that of neon. Trend number 3, electron affinity. If the energy released exothermically, meaning negative, when a gaseous atom gains an electron. So represented by the equation, chlorine atom in a gaseous state gaining an electron to become chloride ion. Electron affinity is negative 349 kilojoule per mole. Electron affinity generally increases across a period because of greater effective nuclear charge. Electron affinity decreases down a family group because of greater electron shielding. Fluorine, being the most reactive nonmetal, has the greatest electron affinity, and that explains why it is so reactive, because it has the greatest ease to gain an electron in a chemical reaction. You might have done the halogen lab before. A student tried to investigate the chemical reactivity of halogens by performing single replacement reactions between chlorine, bromine, and iodine with the potassium halide, that means potassium chloride, potassium bromide, and potassium iodide in different test tubes. Now, to each of the mixture of the halogen halide, hexane is added to detect the presence of halogen molecules because they produce a specific color. It is known that iodine would turn pink in hexane, bromine would turn orange, and chlorine would remain colorless in hexane. We also note that the aqueous solution of potassium chloride is colorless, and so is potassium iodide, but potassium bromide is yellow. Because hexane is less dense than water, it forms an upper organic layer in the mixture in the test tube, while the lower bottom is the aqueous layer. The resulting color then in this test tube can be used to conclude whether a reaction has taken place or not. Now let's look at the data chart that's collected by the student. On the horizontal axis, we have chlorine water, bromine water, and iodine water. And on the vertical axis, we have potassium chloride, potassium bromide, and potassium iodide. Notice I marked an X for chloride and chlorine, bromide and bromine, and iodide and iodide, because there's no reaction taking place. But there are then the other 6 test tubes. Test tube number 1 has orange on top, colorless on bottom. Test tube 2, pink on top, colorless on bottom layer. Test tube number 3, orange over colorless. Test tube number 4, pink over yellow. Test tube number 5, pink over colorless. And test tube number 6, pink over yellow. Now we're going to make use of these to deduce whether reaction has taken place or not. In test tube number 1, when we put the bromide added to the chlorine, it turns orange and colorless, meaning that now the bromine has been formed, occupying the upper layer, and the bottom layer now becomes colorless due to the formation of chloride ion. In test tube number 2, when potassium iodide is added to chlorine, it is pink on top, meaning the formation of iodine, and colorless on bottom, meaning the formation of chloride. In test tube number 3, when chloride is added to bromine, it is orange on top and colorless on the bottom layer, meaning the bromine never changed and the chloride never changed. There's no reaction. Test tube number 4, when potassium iodide is added to bromine, upper layer is pink, formation of iodine, and lower layer is yellow, formation of bromide. So there's a reaction there. Test tube number 5, when chloride is added to iodine, iodine is pink on the upper layer, chloride is colorless on the bottom layer, no reaction. And the last test tube, potassium bromide added to iodine, again is pink on the upper layer, iodine is there, no change, and bromide is yellow on the lower layer, no change, no reaction. So we can actually make use of this to deduce whether reaction has taken place or not. In conclusion, chlorine is more reactive than bromine, which in turn is more reactive than iodine, because chlorine has less energy shells, and therefore it will have less electron shielding effect than bromide and iodide ion. Therefore, chlorine has greater electron affinity to grab or remove the electron from bromide and iodide ion driving the reaction forward to form chloride ions. And a similar argument can apply to bromine in terms of tracking the electron away from iodide ion to form bromide ion. So a lesson summary for today, students have learned using PES data to explain how the energies of electrons within shells in atoms vary and to deduce the electronic structure of an atom. That's a very important learning. And finally, the use of the trend of the electron affinity to explain the increasing reactivity of halogens of the family group. That means fluorine is more reactive than chlorine, which is more reactive than bromine, and more reactive than iodine. From the team of MLCA, I'd like to thank you for watching, and I do hope to see you again next time.